Hello guys, hello world, hello Philippines. This is again, I am a singer, eternal voice. Okay, this moment I will be going to discuss another gas law topic, which is specifically the gas solubility law discovered and formulated by Mr. Henery in 1803. As we can remember, we have already discussed the ideal gas law, the real gas law, okay, the Boyle's law, the Charles law, the Kay-Lussac's law, the Avogadro law, okay, the Dalton's law of partial pressures, okay, like that, and also the combined gas law. This is also an extension for that gas law, but this is solubility gas law. Refers to solubility, meaning there's a solute and there's a solvent. Okay, so the solute will be dissolved in a given solution. Okay, and then this solvent will act to dissolve the solute in a given solution. Okay, so there must be a solute-solvent intermolecular forces or intermolecular reaction during the collision of particles or bombarding of particles. Okay, for example, if we heat the water, okay, a pure water or any kind of water, or rainwater or whatever water, bottled water, if we heat that one, then of course it will vaporize. Some molecules will escape into the atmosphere, right? And then some of the gas molecules will penetrate and will collide to the liquid molecules. So upon collision, okay, and bombarding of those molecules, it will develop an intermolecular interactions. Okay, so the greater the intermolecular reactions, okay, the greater the solubility, something like that. So I will draw to you so that you can simply understand, or we can simply understand what I am explaining to you now. We will illustrate that one, okay, later. Just okay, I will get my pen, something like that. Okay, so first we need to define what is a solubility. Okay, so solubility is the measure of the solute in a given solution. Okay, so this solute must be dissolved in a solvent in a particular solution. Okay, like that. And our solute is specifically the gas, of course, because if your solute is no longer a gas, then this law will not be applicable to this Henry's law. Okay, so it should be a gas is your solute, okay, in a given solution, and you have also that solvent, so solute plus solvent, then solute to solvent intermolecular forces, okay, like that, to cause the higher and greater solubility. Okay, not only that, I will discuss to you further the relationships of the partial pressure of the solvent, like that, the solubility of the gas, okay, in a solvent, and the, of course, since Master Henry discovered this law, so the constant is from him, Henry's law constant, and that could vary according to the temperature. Okay, normally in the problem solving of Henry's law of gas solubility, okay, the Henry's constant is always given. Now, if the Henry's constant is not given, Henry's law constant, then you have to scan for any chemistry textbooks or any source of information in which the Henry's law constant has been tabulated as per its corresponding temperature, something like that, because all solvents of gases have its Henry's law constant, okay, in particular temperature, something like that, if it is not given. But usual situation or problems regarding Henry's law problems are having the Henry's law constant. Or it could have also, you can get the Henry's law constant through that equation. Okay, like that. I can discuss to you two equations, but first I will discuss to you the basic theory regarding Henry's law. Again, what is solubility? Solubility is the measure of the solute in a given solution, and this will be dissolved in a solvent. Okay, so if that is the case, we need to determine the concentration or the solubility. Actually, it has the same meaning, but to be specific in Henry's law, we use the term solubility, not the molarity, molality, or the concentration itself. But sometimes in the problem solving, you will use the word concentration, and do not be confused to that, because some given would be related to Henry's law also. Then you can use the formula of Henry's law. For example, there's a partial pressure like this in a given solution. Solution means solute and solvent, and the solute will be a gas. Always bear that in mind, that the solute is always a gas. Okay? No other. Okay, like that. Something like that. Okay? I will discuss to you. I will draw something. Okay. Okay. We have the glass. This is a transparent glass, for example, and then we have a liquid inside of this. So this is the liquid, okay, like that. Okay, and say for example that you will heat this liquid for a certain temperature. Let take for example only. Okay. Okay. Here is the heat, heating the liquid molecules. So what will happen now? The molecules will escape to the atmosphere. Okay. If the boiling point of this liquid has been reached to, say for example, not for example, but this is really true, this is standard, 100 degrees Celsius, because this is only water. If different solvents or liquids, not water, it will vary the boiling point, not 100 degrees Celsius, but since this is water, the boiling point is 100 degrees Celsius. So what is boiling point? Again, we need to recall in our stock knowledge that the boiling point is when, okay, the vapor pressure of the liquid, okay, is equal to the pressure to the surrounding in this area. Okay, the vapor pressure of the liquid, when it equals to the pressure in the surrounding, okay, that is the boiling point, because this is open, okay, like that. So if it equalizes, then the boiling point has been reached to 100 degrees Celsius. Okay, and then after that, the liquid molecules will escape to the atmosphere. Let's say like this. So okay. So during the boiling point, the liquid particles will vaporize. Okay, and then some of the liquid gas particles, because others are escaping already, and some of the gas particles will be on the downside. Okay, so if it will be in the downside, some of the gas particles or molecules, and there are also molecules of liquid here that does not escape. So these molecules of the liquid here that does not escape yet, okay, say for example you stop the heating when it is boiled, so of course there are liquid molecules still remains here, and then those gaseous particles will remain, not totally escape to the atmosphere, will also go downside here. then they will react with each other. Okay, something like this. Okay. So, like this. Okay. So some of the gas particles that will remain will go downside because not all will escape, right? Because it has been stopped the heating process. And then those liquid molecules will also react with these gas particles. So they collide with each other and bombarded with each other. So in that situation, we have now what we call as IMF, the intermolecular forces between the gas particles and the liquid water molecules. They are reacting with each other, bombarded with each other, collided with each other, and they have an intermolecular forces. Since Henery's law is referring to solubility, okay, so there's a ratio of solute and solvent somewhere here in this portion. So solute and solvent intermolecular reactions is in this point, okay? So the more intermolecular reactions between the gas particles and the liquid molecules, then the higher the solubility, okay? The higher the solubility. So in Henery's law, the higher the solubility, okay, meaning to say the higher the intermolecular interactions between the liquid particles and the liquid molecules, okay? That like that. IMF higher, IMF intermolecular forces or interactions, and then higher solubility. Okay, now since the volume is going downward, okay, since the volume is going downward, okay, what causes the volume going downward? Because it undergoes the process of evaporation, okay, and the liquid particles has been vaporized, some of it, right? And now the volume will become less, okay, like this. Okay. This is the heat. Okay. So we applied heat because this is boiling process, right? So if we apply heat, we known as temperature. Okay. During the process, we assume the temperature is constant. That is in Henery's law. Because we leave the heat is in constant for this because it's boiling process. Okay. It doesn't matter, we will not adjust the temperature because it's boiling. Our purpose only is to boil the water, okay? So the temperature is constant, okay? While it's being heated, it is understood that the volume will be decreasing, okay? When the volume will be decreasing, okay, the gas particles will go up and some of the gas particles will interact to the liquid particles here, and then the volume will goes downward. The more the volume will goes downward, the more there will be an intermolecular forces or intermolecular reactions, then the solubility increases. Okay, the solute to solvent intermolecular reactions will be higher and the solubility also will be higher. Okay, now this is the time Henery's law formulated one variable pressure also, partial pressure of the solute. Okay, the partial pressure of the solute, if higher, for example, if the volume is lower, because the more the volume will be lowered, the higher the pressure on it, right? Basic theory. The more pressure involved in a particular system, the volume will go down. Okay, that holds true in this illustration also. That if the volume decreases, that is due to the higher pressure applied, because also there is higher temperature during heating process. So temperature and pressure is inversely proportional with each other. The more you applied heat, the temperature goes higher, of course, by theory, the pressure will goes higher. So we need more pressure and high pressure in order for the volume to be reduced, and that's the time the solubility will be higher and higher and higher, because the more the gas particles and liquid molecules of the water will be interacting with each other, so higher solubility. Now, we introduce the pressure here. Okay, we increase the pressure. Let's say arrow up. Okay, arrow up, pressure. Since you decrease the volume, okay, since the volume is decreased, since the volume is decreased and the pressure is going up, because the temperature is also very hot already, okay, it's very hot already, so the pressure will like this, okay, then our solubility will be higher. So therefore pressure will be directly proportional to the solubility, like this. Okay, let's forget the drawing and then show another paper like that. Okay, so the pressure will goes up. Of course, your solubility goes up also. Solubility represented capital S. Okay, like this. And then your IMF and intermolecular forces or interactions, or what we call as solute-solvent intermolecular reactions. So like this. So if your pressure goes high, this is the general conclusion of Henry's law. If your partial pressures goes up, okay, your intermolecular forces or the solute-solvent intermolecular reactions will also be higher, and your solubility will become higher, getting high, because the more it will collide each other, the liquid particles and the gas particles, okay, collision with each other, and the volume will decrease. Okay, the volume will decrease. Never mind with the temperature, because the temperature is to be constant in this law of Henry's law. We did not account the temperature. We will account the only in getting the Henry's law constant. Now, through this theory, Mr. Henery formulate the equation, which is solubility. Okay, solubility of a gas is equals to Henry's constant K of a gas times the partial pressure, okay, of a gas. So this is now our formula for the Henry's law. Solubility of a gas is equal to the Henry's law constant kg times the partial pressure G. G means gas. Okay, remember, that's gas, not solvent. And it's very important to take note that during the problem solving, because you will get confused. Sometimes you will use the partial pressure of solvent like that, but it is not. It is a partial pressure of a solute, okay, or the gas, okay, gas, usually the solute here, okay, and the Henry's law constant of the gas and the partial pressure of the gas. So if there are conditions that you need to assume, blah, 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 then you have to just understand and analyze the problem. Something like this. It goes like this, a formula. Basic formula, equation 1 for solubility formula. Okay? Like that. This is equation 1. Okay? So in this manner, we can say that Henry's law constant is equals to G solubility gas of the gas, the partial pressure of the gas. So like this. If you compute for the Henry's law constant Kg is equals to the solubility of a gas over the partial pressure of the gas. So we can say directly that the Henry's law constant is inversely proportional to the partial pressure of the gas. The more, the higher the Henry's law constant, the more lesser our partial pressure of the gas, or the reverse will holds through. If the partial pressure is higher, lower our Henry's law constant. what will happen to our solubility? So that is directly proportional with each other, the Henry's law constant and the solubility constant, like that. Okay, like that. So in this manner here, the solubility is directly proportional to the partial pressure. Okay, like this. Okay, very clear, something like that. Now I will illustrate. For example, at an initial stage, we have, oh my god, no more. For example, this one. Okay, for example, in an initial stage, we have a solubility of, for example, the atomic gas, which is carbon dioxide. So we have partial pressure initial of carbon dioxide, let's say CO2, is equals to 0.03 molar or moles per liter based on our knowledge and basic chemistry. Okay, like that. Okay, this is the solubility S1, and then the partial pressure is, let's say, 1 atmosphere. Okay, and then if we have a final stage of 2 atmosphere, okay, like this, what this X all about. Okay, so for example only, okay, we have a initial solubility of carbon dioxide. This is carbon dioxide, diatomic gas. Okay, our initial solubility is 0.03 molarity or moles per liter. Or it could stated be as a solubility in the problem, or it could be stated as a concentration, or it could be stated directly as capital M, or it could be stated as moles per liter. It's just the same. Okay, if you are just having an alertness and quickness of your analysis, it's just the same. Okay, do not be afraid for the state wording or statement. Okay, and then at initial pressure is 1 atmosphere. So at a final partial pressure of 2 atmosphere, so this will be doubled, okay, by 2, because of the concept that the pressure goes higher, the solubility also goes higher. If we double, okay, the pressure, the molarity, will also doubled, or the solubility will be doubled. Okay, like that. But don't worry with the molality. Molarity are just the same with the solubility. There's a solute and solvent behind. So that's we need to understand also. Maybe there are problems also given molality, right? In kilograms per liter. Okay, kilogram per liters of solution. Kilograms of solute per kilograms of solution is our molality, and our molarity is the liters of solute per moles of solute per liters of solution. Okay, like that. So moles per liter. If you forgot the numerator and denominator of the formula for the concentration or the solubility, just take note the unit. That is your identification. So usually concentration in molarity expressed in moles per liter, then you can say that it is moles of the solute per liters of the solution, because concentration involves always a solution, meaning the moles of a solute plus the moles of the solvent, like that. And through that, you can have the basis of calculation for that also, and we have also the atomic weight or the molecular weight, then we can compute for that. Okay, since partial pressure, then it is very important also to determine the total pressure and the individual partial pressure, and through that we can determine the mole fraction. Okay, because in Dalton's law of partial pressure, if we connect that here in the Henry's law, okay, we can get the mole fraction of partial pressure to the total pressure. Okay, since we have that already, since our formula for solubility for Henry's law involves partial pressure, then there is also a time that total pressure will be given in the problem. Since you will forget that Dalton's law of pressure anymore, then you will be trapped in the solubility problem because it is connected. As I said before, all formulas in gas laws are interconnected with each other. You can formulate your own formula and derive out of it if you cannot understood what's really emphasized in the problem. For example, if you already have the formula of this Henry's law with the solubility of a gas is equals to Henry's law constant times the partial pressure of the gas, and then you forgot the formula, then even though you will substitute, you cannot still get the answer. So that is understood that there's another formulas that will be tried to link with that particular formula. So that's the secret for that. Okay, there is also another formula for this by Henry's law. If we take the final and initial stage, now we get that one directly. We have no more time. So P2 over P1 is equal to S2 over S1. Okay, like this. This is another formula. This is equation 2 for Henry's law. So this is the equation 2 for Henry's law. Partial pressure